Is you press go?
Yes.
Okay. So, my children. So, redox quiz tomorrow. Okay? Just the basic stuff, like here's what happens in reduction, what happens in oxidation. Be able to do like the half reactions. So for example, if you get one like this one on number 6 on that practice sheet of equations from yesterday. So when you get a situation like number 6, okay, first off, you got to figure out what's your spectator ion, which ones do you not have to worry about. So if you look at number 6, let me kind of give you some hints. So you have a solution of sodium iodide, okay? So when you have sodium, all the sodium is doing is basically giving us a carrier for the iodine, okay? So, because I can't go into the storeroom, I can't send Evan into the storeroom and go, hey, Evan, go get me a bottle of iodide ions, okay? They don't exist in the solid form as an iodide ion. Now, I can say, hey, go get me a bottle of sodium iodide, and I can mix that up in water and create sodium ions and create iodide ions, okay? And there's a big difference between the two, okay? So this is why when you talk about the sodium iodide, because it's a solution, these are going to exist as sodium ions and iodide ions. It's not elemental sodium, it's not elemental iodide. Huge difference between the two. Evan.
So what would happen if you got like, in like a vacuum chamber, you had like a bunch of iodine, and then you just like put a bunch of electrons on it?
Nothing.
So it wouldn't ionize?
No, because it's still going to be bound together as solid iodine. That lattice structure bonding is going to be stronger than the tendency to take in an electron and turn into an ion, because you still have to break the bonds and hold them together as iodine. And just the addition of electrons is going to do that. Okay?
So what would the electrons do?
No, absolutely nothing. So they'd be like, cool. Because they're going to run into the electrons around the electron cloud of the existing iodines, and they're just going to repel each other. Because they all have the same charge. So, valid question. Okay. All right. So, then you've got an acidified solution. When you see acidified solutions, that's just code for the fact that we're going to have a bunch of hydronium ions. And that acidified solution typically comes from the addition of like sulfuric acid, nitric acid, hydrochloric acid, something like that. But you want to pick an acid that, number 1, is a strong acid, number 2, has an anion that isn't going to interfere with the reaction itself, okay? So like this one, I've got sodium permanganate and sodium iodide, okay? I would not choose hydroiodic acid to put in there, because that's just going to add more iodine ions to it. I might pick nitric acid. Oh, pretty benign. I don't have the nitrates aren't part of the story. I'm just going to add those hydronium ions. Then you've got sodium permanganate. Okay, hey, sodium permanganate. Okay, again, don't care about the sodium, not part of the story, because I can't get just permanganate ions. So basically, the nuts and bolts of this, the only thing that I'm going to worry about are those iodide ions, those hydronium ions, and that MnO4. Okay? Those are all the ones I'm going to worry about. So then from that, you're not told what the products are. So you just have to know, oh, MnO4 is going to change into Mn2 plus. Okay? That's just that's the way it goes. It's going to go all the way from 7 plus down to 2 plus. So this is 7 plus, that's going to be 2 plus, so that's going to gain 5 electrons. So in terms of terminology, if you look at that sodium permanganate, is that a good reducing agent or is that a good oxidizing agent?
Oxidizing agent.
Why?
Because it itself is being reduced.
Yeah, so the sodium permanganate is going to contain the element, which is manganese, that really wants to gain electrons. So that's one of the most biggest hang-up kids get. So when you see reducing agent, sometimes called a reductant, it means the same thing. So reductant reducing agent contains what is oxidized. The oxidizing agent, sometimes called the oxidant, contains what is reduced. Okay, so they're like flips of each other. Okay, so a lot of this unit is going to be terminology. Like today, we're going to introduce cathodes, anodes, salt bridges, tendencies of all of those. So if you want, if it were me, okay, because this unit probably about as specific in terms of terminology as any other unit that we're going to have. If you want to start a bank of index cards, say, okay, hey, this is my anode. What happens at the anode? This is my cathode. What happens at the cathode? Okay. What is a reducing agent? What is an oxidizing agent? Where are reducing agents found on the redox table? Where are oxidizing agents found? Okay. So the more, and personally, if I wrote things down, I'm much more reluctant or much more likely to remember them if I don't, because that's just how I'm wired. I like to draw pictures, I like to write things down. You don't have to, but that just might be a suggestion. Okay, so this has to get electrons from somewhere, okay? It has to. So what's going to happen here is that it's basically, this is going to come up, and the only source from this is the iodide ion. Why can't the hydronium ions give up electrons?
They don't have any.
They don't have any. It's a proton, okay? It cannot, the hydronium ion cannot give away electrons because it doesn't have anything to give, right? It's already just tapped out, okay? Doesn't have anything to give. So the only thing at best the hydrogen can do is take in an electron and form hydrogen gas, but you're not told that you form hydrogen gas. So basically, the MnO4 is going to turn into Mn2+. Now, this is a situation where you've got to balance the electrons. Oh, I got 5 electrons here, okay? Then I've got 4 oxygens, so I'm going to put 4 waters over here, and then I'm going to put 8 hydrogens over here. Now, at this step, if you do it right, what should happen? Should be balanced. It should be balanced in number of particles, and it should be balanced in charge. So on the quiz tomorrow, when you do these half reactions, ask yourself, wow, is this balanced? If it is, at least you got a fighting chance. If it's not balanced, it's wrong, okay? And don't sit there and go, oh, it's okay, it's not balanced, it's not that big a deal. Okay, you have violated the law of conservation of charge, okay? It's a law. It isn't just,
You should get a sticker, like a stamp.
yeah, it's a law. Boom. Okay, anyway. So then you got the iodine. So here's what you do wrong with the iodine. You go, oh, iodine is going to turn into I2. And you're going to sit there and go, oh, that's just 1 electron. And I'll just put 1 electron over there. It's cool, right? It's balanced. Is it balanced?
Iodine.
No, I got to have 2 iodines, which means then I also have to have 2 electrons, okay? Now, what's the least common multiple of 5 and 2? 10. So I'm going to multiply everything here by 5. I'm going to multiply everything here, that one by 2, this bottom one by 5. Then I'm going to add them together. So if all goes well when you add them together, what should happen?
Electrons cancel.
Electrons cancel. That's one thing. You should balance on,
Charge
and you should balance on number of particles. So if you go through here, and if you look at this, right, everything balances out. You've got 16 hydroniums here. You've got 8 hydrogens over there because you have 8 water molecules, so that gets you to 16. You got the 2 MNs. I got the 2 MNs. I got 8 waters. I got 8 waters. I got 10 iodines. I got 10 iodines. I add together all the charges. They sum to each on both sides. Okay, so that's how you can check that you got that right. So if you hand in that quiz tomorrow and you haven't added a half reaction reduction and a half reaction oxidation to get a big equation like that, you have done something wrong. Okay? Tell you that straight up. Okay, when you get to number 5, okay, the halogens are their own reactivity series. Fluorine, chlorine, bromine, iodine. The most reactive halogen is at the top. Now, this is going to be important later on. Non-metals, especially the quintessential ones like oxygen, fluorine, chlorine, they're halogens. Those react by taking in electrons. Okay, that's how they react. Metals, especially like the alkali metals and rare earth metals, those react by giving up electrons. Okay, so basically, the more willing an atom is to give away its electron, the more reactive it is. The more willing a non-metal is to take in electrons, the more reactive that is. So if you view this from the perspective of a redox reaction, the non-metals, oxygen, fluorine, chlorine, bromine, okay, they're willing to take in electrons. Okay, they're willing to take in electrons. So are the non-metals likely to be reduced or oxidized? Gracie.
Yes.
Are the non-metals, which are looking to gain electrons, are those likely to be reduced or oxidized?
Reduced.
Right. Because they're likely to be reduced, EMA, are non-metals oxidizing agents or reducing agents?
Oxidizing.
Fantastic. Okay? So elements on the far right side of the periodic table want to gain electrons, they want to be reduced, they're oxidizing agents. Now, you have the metals, classic ones, lithium, okay? Your alkaline metals, your rare earth metals. What do they want to do?
Give up electrons.
They want to give up electrons. They want to get rid of their goods. Because they want to lose electrons, they want to get oxidized, so therefore they are reducing agents. Okay? So if you look at the most reactive metals, they're at the bottom of that group because they're most willing to give up those electrons. Okay? And that has to do with Coulombic forces and how far away they are from each other. So what would happen on number 5? Okay? You would take chlorine gas, which is highly poisonous. If someone says, offers you like, hey, breathe this, it's chlorine gas. Don't do it. Okay? It's bad.
What will happen?
It'll basically get into your lungs and wreck your lungs. Bad
But
for
like you won't die?
Oh yeah, you will
Oh.
if you breathe enough of it.
Just
Okay.
enough.
You'll die from water if you take in enough of that too. So
You're what? You'll drive in water?
you'll die from water if you take in enough of it.
Oh, I was like, drive in water? Why would I drive in water?
Okay, now, so what would happen is that you would have a container of chlorine gas. You would have a solution like of sodium bromide, something like that. You would have these bromide ions floating around. So if you bubble this through, what would happen is that you would see chloride ions, okay, so you would see an increase in the concentration of chloride ions, but then you would begin to see bromine. So the cool part about bromine and iodine is that they both have this distinctive brownish color. So what you would see as this reaction took place, you would begin to see that solution turn brown because of the fact that you are forming elemental bromine. So you would see the bromine itself, the ions, doesn't have a color. Okay, it's colorless, like salt water. Okay, you can't see anything. But if you form elemental bromine, then you're going to see a distinctive color begin to appear. Okay, so number 3, you have to know your solubility rules. Okay, that's it. The whole key to number 3 is your solubility rules. All chlorides, bromides are soluble except for basically silver and lead. So that's how I knew I was going to form a precipitate of silver bromide. You just have to know that. 2 is a classic redox reaction. Okay, and now keep in mind tomorrow, you will have the periodic table with the reduction table on the back of it. Okay, you will have that, right? You just have to be able to know how to use it. So if you look on this one, and again, you can look at E naught values, you can play the over-under game. I don't care. But you look at zinc relative to copper. These are copper ions. This is not elemental copper. You know, copper ions are basically going to come up to the zinc and go, yo, so, give me your electrons. The zinc says, fine, I don't want them anyway. Copper becomes more stable. You begin to form elemental copper, and the zinc ions are going to go into solution. Talk about number 7. 7 is old school. Solution of sodium acetate and nitric acid are mixed. So basically what you need to realize here is that, oh, sodium acetate, oh, that's the anion, off of a weak acid. I'm going to introduce nitric acid into it. Nitric acid is a strong acid. In other words, it's going to have an abundance of these hydronium ions. They're going to hook up together, and you're going to form the weak acid of acetic acid. Okay? There you go. 8, iron nail, less in solution copper dechloride. Don't care about the chlorides, it's a soluble ion. It's going to be a spectator. It's a redox reaction. 9 is a redox reaction. So on number 9, and you're specifically told a piece of solid calcium is heated in oxygen gas. So basically, you're going to burn calcium. Okay? That's what you're going to do. All right. And number 1, where it says ethane is burned in air, air is the magic code for, it's going to react with the oxygen in the air. Thank God it doesn't. Thank God nitrogen is relatively inert. It doesn't react like oxygen did. Because if you look at the percentage of our atmosphere, we're like 77% nitrogen and about 22% oxygen. If those are reversed, and thank God it's not, because I promise you we probably wouldn't be here having this discussion. If we were 77% oxygen and 22% nitrogen, imagine how hard it is to put out a fire at 22% oxygen, because typically your oxygen is your limiting reactant. If our atmosphere was reversed and we had 77% oxygen, anytime you would start a fire, basically you would never be able to put it out. Okay? There would be no candle sales. Candles, go, it's up! Okay? Can't have that. Wouldn't work. Okay, everybody cool with that? Got that? Okay. All right, let's go to the back. Bring that camera.
Okie doke. I don't know, it seems shorter. Don't you think?
It is. Okay, you take it. Tell Skippy.
Okay.
Hey, Zach.
Somebody a little shaky base here. All right.
He's not going to watch it. Everyone knows.
So those whole things, these are known as voltaic cells. So on a voltaic cell, and again, this is going to come down to the terminology. So I've got a strip of zinc, and to that I'm going to add zinc nitrate. Put that in there. And then to that I'm going to the other one where I have copper. I'm going to add copper nitrate. Put that in there. Okay, flush that. Now, to this, over here, I have what is known as a voltmeter. Okay? So, voltmeters, oddly enough, measure in volts. Shocking idea. And so, let's say, for example, I've got your basic little battery. And if I touch that to the leads to the battery, I get about 6.25 volts. So volts, when you get to electricity, you can imagine voltage as being here's a dam that holds back water. So your voltage is basically how high the water is behind the dam. So if your battery, if that battery is fully charged, you got 6.25 volts, okay? Now, volts are also known as joules per coulomb. So coulomb is the basic measure of charge. Each electron, proton in the world that we've ever encountered in this universe, every charged particle has a charge of 1.6 times 10 to the negative 19th coulombs. Okay? Don't worry about that number for now. We're going to get to it later. Okay? But every particle, charged particle that makes you up, every electron, every proton, has the same amount of charge of 1.6 times 10 to the negative 19th coulomb. The exact same. Okay? So, when you look at 6.25 volts, joules is a measure of energy. So this is how much energy you have per unit of charge, okay? So volts means joules per coulomb. That's why we talk about like how high that water is. The other thing when you get into electricity, you talk about current, okay? So current is basically the flow of electrons. So imagine that we have this dam, and we have two options. Option number one, we have this tiny little straw that goes from the top all the way down to the bottom. Option number two, we have this big, massive concrete pipe, okay? They both have the same voltage. Water has the same potential to move. But the little straw here isn't going to allow very much water to go through. Big pipe, much bigger current, is going to allow a lot more water to go through. So the last one we'll talk about is resistance, okay? So resistance impedes the motion. So imagine that you have like that straw, but it's like lined with sandpaper, okay? So it's really, really tough for that water to flow through. So resistance is basically a measure of how impeded that flow is, whether it's electricity, whether it's water. Okay, so that's your basic terminology. So what this is going to measure is how much potential there is for the electrons to want to move from one place to another. Okay, so when you set up a voltaic cell, there are certain things that you have to have. You're going to have an anode, you can have a cathode, a salt bridge, and a voltmeter. So when you do this, what the voltmeter is going to do, I'm going to hook this up, and for now I'm just going to randomly hook the copper up to the lead. I'm going to hook the zinc up to black. And you'll notice on the voltmeter that my voltmeter is reading 0, okay? So right now, even though I've got it hooked up, the electrons have no potential to move, okay? Nothing there. But I'm going to take my salt bridge. So my salt bridge, and sometimes you'll see this drawn differently. We're going to use just a piece of litmus paper, and we're going to soak that into potassium nitrate. So what the salt bridge does is that allows ions to flow through. But you don't want to pick something for your salt bridge that's going to be in either one of the cells. You want to pick something that's inert, it's there, it can react, but you don't want it to interfere with anything. So I'm going to take this, and we're going to drape this across from here over to here, okay? Now, as soon as I do that, as soon as I put that salt bridge in, I get a voltage reading of about 0.92, okay? So I went from 0 to 0.92. Now, as soon as I take that salt bridge out, my voltage drops back down to 0. I put the salt bridge back in, voltage goes back up. Now, here's the most common misconception about salt bridges, okay? The electrons do not flow through the salt bridge, okay? The salt bridge is like Switzerland in World War II. The purpose of the salt bridge is to maintain neutrality, okay? What the salt bridge does. So get this out of your minds right now. The salt bridge is there. It's important. The cell won't function without it, but the electrons do not flow through it. The electrons are flowing through this external circuit around here and back like this. That's the direction of the salt bridge. Now, somebody go get that half reduction chart. Hello?
Hey.
Hey.
Are you using the lab quest for fourth block?
No.
Okay, I might come get yours because I can't find the other part.
Okay. So, what we need to figure out is that we're going to start with, let's go alphabetical. Let's start with copper. So, what's the reduction potential from Cu2 plus gaining 2 electrons, turning into elemental copper? What's that value? 0.34 volts. Okay? So if copper is reduced, gains 2 electrons, turns into elemental copper, I have a value of 0.34. Now, as it's written on there, what's the reduction potential for zinc? Way down there at the bottom.
Negative 0.76.
Negative what?
0.76.
Negative 0.76 volts. Okay. Now, if all you saw was this, you don't know anything else, this is all you saw, which one do you think is going to stay as a reduction, and which one's going to get flipped and turned into an oxidation?
Zinc's gonna flip,
Why?
because it's negative right now, and Mother Nature doesn't like that.
Bingo. Mother Nature wants this to flip over. So copper wants to take in the electrons. Copper's like, man, those are my 2 electrons. I want to get them back, right? So copper is going to take in these electrons. The zinc goes, I don't care about my electrons. Take them, I don't care. So the zinc is going to turn into Zn2 plus 2 electrons. And then as soon as I flip it, notice that this becomes a positive 0.76. So here's my question. In this cell that has the copper and the copper ions and the elemental copper, what's happening here? Reduction or oxidation? Is the copper taking in 2 electrons and turning into copper, or is the copper turning into copper ions?
Copper ions are turning into copper.
Yeah, because this is the direction this thing wants to go, right? So what's happening here is the Cu2 plus is taking in 2 electrons, it's forming copper. So here's how we can know that. If we let this run long enough, if we weighed the mass of this strip over a period of time, you would see the mass of this strip increase. Because you're taking from copper ions and turning it into elemental copper. Okay? What's going to happen to the concentration of the copper ions over a period of time? It's going to decrease. Cool. Okay. Now, so this is reduction, right? So later on you'll see the easiest way to remember this. This means this is the cathode. Okay? If you're a cat person, okay, this is the red cat. Okay? Because reduction happens at the cathode. Okay? Red cat. Boom, there you go. Now, over here, I got zinc ions and I got zinc. Oh, on this side over here, Mother Nature's going, man, if this copper is going to take in the electrons, it's got to get electrons from somewhere. And the zinc goes, hey, I got 2 electrons that are annoying as all get out that I really want to get rid of because I don't like them. So Eddie and Edna, my 2 external way far electrons, take them. Copper's over here going, it's like a party. So what's happening is the copper ions are over here, if you give a high school party analogy. So the copper ions are over here going, yo, sup, we got this cool party going on. And the electrons are over here and they hear this, okay? They hear the call with the party siren. And they go, oh man, this is cool, okay? Let's go over there. Now, so what's going to happen is that the electrons are going, ooh, this sounds like a good time. So the electrons go to the zinc and they go, deuces, we're out. Because this is a better party over here than what you all have going on. Okay? Screw you, we're out. So what's going to happen here is that the zinc is going to turn into zinc ions and 2 electrons. So what's happening here? Reduction or oxidation?
Oxidation.
Oxidation. So this is going to happen with my oxidation. Okay? So this is what we call the anode. So if you're into remembering things in terms of atoms, this is reduction. It's the red cat. Okay? Reduction and cathode. This is anox. Okay? Anode happens with the oxidation. Okay? So if you're an animal lover going, oh, red cat, anox. Now, if you're a linguistics person, what do A and O have in common?
Vowels.
They're vowels. Okay? The vowels stick together, and then the reduction of the cathode, the R and the C are Consonants. Oh, so the consonants stick together and the vowels stick together. So if you're a linguistics person and you want to remember, oh, the vowels stick together and the consonants stick together, go with that. If you're an animal person, think of that. If you're a mathematical person, look at the chart. Oh, which one wants to go in this direction? Which one has a positive E-naught value? Which one wants to get flipped? You can do that. If you're a gambling person, you look at the chart. Oh, let's bet the over-under. Oh, copper is the over, zinc is the under. This goes in this direction. That gets reversed. I don't care. Pick one. Doesn't make me neutral. Okay. With all that said, now, so the anode is oxidation. Now, here's my question. The electrons are moving, and we know that because of the fact that we have this voltage. We've got a voltmeter that's measuring voltage, right? So what this is going to tell us is that these electrons have a desire to move. So the question is this: do the electrons move from the zinc to the copper, or are the electrons moving from the copper to the zinc?
From the zinc to the copper.
Why?
Because on the reactions over there, the copper is gaining electrons and the zinc is losing electrons.
Fantastic. So what's happening, again, if you go with the party analogy, the copper ions are over there going, ooh, big party. Electrons are over here going, see ya, gotta go. So the electrons are going to move in this direction through the voltmeter, not through the salt bridge, okay? Not through the salt bridge. So, in terms of the movement of the electrons, this goes like the alphabet. The electrons goes over here, we said this is the anode, right? So it's like the alphabet. Electrons move from the anode to the cathode, okay? So it's just like the alphabet. Oh, A comes before C. Electrons move from the anode to the cathode. No exceptions, zero, zip, none, okay? So, electrons move from the anode to the cathode. So let's talk about the salt bridge, okay? Salt bridge, pretty important. Because as soon as I took that salt bridge out, the reaction stopped. So the purpose of the salt bridge is to maintain neutrality. So this salt bridge is made up of soluble potassium nitrate, which means this is existing as potassium ions and is existing as nitrate ions. Cool with this. Now, here's the deal. Over here, in my anode, am I increasing or decreasing the number of zinc ions? What's happening to the concentration of my zinc ions as this reaction goes by? It's increasing, right? So I'm going to increase the concentration of my zinc ions, right? Okay? Because I'm creating, oddly enough, zinc ions. Oh, great. Zinc ions are going to increase. Over here, what's going to happen to the concentration of my copper ions? It's going to go down. It's going to decrease my concentration of my copper ions. Cool. Now let's look at this. So I'm increasing the number of positive charges, right? Increasing the concentration of my zinc ions. Because they're giving up their electrons. So what's going to happen to the mass of this zinc electrode over the period of time? So decrease, because it's going from elemental zinc into the ions. Okay? This mass is going to decrease, the concentration of my zinc ions is going to increase. So I'm increasing the positive charge over here. So if I want to maintain neutrality, okay, if I want to maintain neutrality, do you think the nitrates are going to flow to this side, or do you think the potassiums are going to move to that side? Nitrates, why? Because they have a negative charge to balance out the increase in the
Positive.
So my nitrates are going to move in this direction. Yeah, okay. Now, stop. But go harken back to your Chem 1 days. What's the generic term for a particle that has a negative charge? Anions. Oh, the anions move towards the anode. Woo, how cool is that? Wow. Now, over here, what am I doing to the number of positive charges in this solution? It's decreasing it. So what's going to happen? The potassium is going to go over here to make up for the decrease in the positive charges, right? So the potassium is known as a cation, oddly enough. So the cation moved towards the cathode. Oh, how cool is this? Okay. Now, so the reason this happens, when I pull this out, okay, when I pull that out, the reason that voltage drops to 0 is because this solution, these two cells become so jacked up in terms of concentration. It becomes so far out of chemical equilibrium that the reaction basically stops. Like, okay, it basically says, I can't deal with this. Okay, I'm just going to stop. But as soon as I put that back in and allow that to maintain that neutrality again, now I get my voltage. So that's why everybody thinks, oh, great, the electrons flow through the salt bridge. It's not the story, okay? There are no electrons moving through the salt bridge. Are ions moving out of the salt bridge? All day long. But the electrons are actually moving through this external circuit. Evan?
So if you did not have like a copper wire or something between the vials, nothing would happen?
Nothing happened. Because it would be like, imagine that over here this copper really wants to have a party, but it has no way to communicate that information to the zinc ions. Okay? What was that?
They have no car.
They have the car or cell phones.
Yeah.
Not even smoke signals. Old school. Okay? Couldn't even pass them a note. They got nothing. Okay. So that's why I said you have to know this terminology.
Figure out electrons.
Oxidation, cathode, you got anox, red cat, vowels, consonants, over, under, mathematical voltages. I don't care. Okay? Now,
What is it?
the other thing that, if you've ever looked at like a battery that has positive and negative charges on it, so the cathode is the one that's going to have the positive charge. That's the easiest way to remember that, because that has like a plus sign in it. Okay? So that's the easiest way to remember that has a positive charge. Okay, got it? Good? Grand? Now, one last thing.
This is a very, like,
So
You
over
know?
a period of time,
exciting lecture. Yeah,
What?
I feel like you're, like, emitting excitement, you know? I don't know. It's like a compliment. I like it. It's kind of, it's very, like, wow.
okay. By the way, is anybody in May South in, well, I got an email from the May South discussion that happened during Encore about my grade here. No, yeah.
I'm like,
Huh?
That was key.
Was it
Keaton?
Yeah. Yeah, it's like, it's weird looking at pictures of Burkamp without gray hair. Oh, it's Keaton? I'm gonna have words with that.
Aw.
Red and green again.
I could, not going to. Okay, so over a period of time, what's gonna happen to the concentration of the zinc ions?
Increase.
It's gonna increase. What's gonna happen to the concentration of copper ions? So what do you think, if we let this run for a while, what do you think is gonna happen to that voltage? Increase, decrease, stay the same?
It's going to slowly decrease until it's 0.
It's gonna decrease. Why?
Because there's going to be less difference.
Yes.
If you
Yeah, so basically what's going to happen is you're going to run out of ions over here going, hey, come party with us. Eventually the copper ions are going to quit talking. The other thing that's going to happen is that this is getting very, very crowded with the zinc ions. Okay? It's very crowded. So it's tougher and tougher for the zinc ions to go into the solution. And it's tougher and tougher for the copper ions to pull those electrons because you have a fewer number of copper ions to do that. Got it? Good? Grand? Okay, back we go.
Say hi to Jamie. Hi, Jamie.
Hey, Jamie.
Hey, Jamie, miss ya.
That would be such a jump scare.
Put it in my mouth.
Okay, give me 1 second. I gotta put on a copy of this stuff.
To be
Action.
here till 6:15 again.
He won't. He probably won't even post this till tomorrow morning.
Kyle Grill also said over there.
How's your day?
Mine? I've had an amazing day. I woke up today. Guys, say hi.
Hi, nobody, because we know you're not actually watching these.
That's tragic.
Dude, I watched
I watched all of them when I was.
Okay, bye, guys.
I'm gonna kind of go old school.
Go old school, like no calculator?
Oh, no, like you've got to do gravity calculations.
Oh, that's fine. I like those. Those are easier than
Okay.
whatever we do. I don't even know what the heck is going
Okay,
on.
now, if you look at the numbers that we just had, so the Cu2 plus gained 2 electrons, and that had a value of 0.34 volts, right? Then the zinc got switched and turned into Zn2 plus ions plus 2 electrons, and that had a value of 0.76 volts. And if you add those together, you get 1.10 volts. So 1.10 volts is the theoretical value of what that voltmeter should have read, based upon standard conditions, okay? And under standard conditions with solutions, you are assuming that the copper ions and the zinc ions, under standard conditions with solutions, the concentrations of both of those are exactly 1 molar, okay? Under standard conditions, 1 molar solution. You assume the temperature is 25 degrees Celsius. So standard conditions with solutions are 1 molar, 1 atmosphere of pressure, 25 degrees Celsius. Now, what's weird is that gas laws have different standard conditions. Standard conditions with gas laws is 0 degrees Celsius, okay? Which really sucks for solutions, because what happens at 0 degrees Celsius?
They're not solutions
Freeze.
anymore.
Yeah, they're not solutions, they're gonna freeze. So it's like, okay, that lab would have been tough to do with the frozen chunk of solutions, okay? Wouldn't have worked. But for whatever reason, they can't get the Scooby snacks together. It's like, can we split the difference and call it like 12? No, it's 25 root 0. So, Evan,
What does putting ions in do to the freezing point of water?
it actually depresses the freezing point, makes it lower.
Ah.
It's called a colligative property. Okay, you can actually use that freezing point depression to determine the molar mass of the ion, but that's a nice story. Okay, so typically what you see, so if you look at what we did when we hooked that up, we had actually 0.92 volts. So that 1.10 volts is an absolute best case scenario. Concentrations are exactly 1 molar, and you're assuming that there's no resistance within the wires. So when you actually hook these up and you build these cells, typically your voltage is less than the theoretical value because there's some internal resistance within the wire. The concentrations of the solutions are always changing because that's what we talked about. So if you were to look at this as like a function of time, is that, let's say you start off here at 1 molar, which is the concentration of the copper ions and also the concentration of your zinc ions. Well, what's going to happen over a period of time is that your copper ion concentration will drop like this, okay? It's going to decrease because it's taking those copper ions, it's taking 2 electrons and you're forming element of copper. Your zinc ion concentration is actually going to begin to increase. So your zinc ion concentration is going to go up, your copper ion concentration is going to go down. And the further apart they get, the smaller that voltage is going to be because there's less of a desire for those electrons to move. Okay, I'm done. So this is out of your book, okay? But now I got to explain some things about these different questions. So
44.
That's how I feel like this is everything now. Because I wrote one thing.
We didn't have this. It was just that, right?
Yeah. Oh yeah, I need that. The last one.
Yeah, I don't know if we did anything. So I was like talking with Sam, and then after arguing, I was like, well,
He just said that it was based on our process. He said, oh yeah, the whole point is you're going to contradict yourself the whole lab. And I was like, oh, okay.
Even less applicable.
oh my god, we're on chapter 20 of
It's an arrow going down. From 13 to 14?
Show reaction.
The word in between. 8, 9, 1, and 20 to 1.
Yeah, it's an and sign, right?
8, 9, 1?
That's not, okay, 9, 1.
Okay, so let me explain this, what I've got here. So, chapter 20, so you're going to do 3, 4, 13 through 16. On 13 and 14, only do A through C. Okay, so on 13 and 14, only do A through C. That'll make sense when you look at that problem. Okay? When you get to 26, 26 are, you're going to have to do half reactions. Okay? So on 26, number 1, only do A and C. Okay? Don't do B. Okay? Just A and C. Not A through C, A and C. But on those, I want to see the half reactions. I want to see the reduction half reaction, and I want to see the oxidation half reaction. Okay? And then 27, 28, 30.
I
So,
was looking for these.
there you go.
It's like, where did my research stuff go in? What's in my
So, on 26, do they give you the odd answers or the even answers with this book? Okay. So let me give you some hints on 26. If 26A goes well, okay, on 26A, if you do that right, you're going to have 4 water molecules, okay? When you get the overall balanced thing, you're going to get 4 waters. On 26C, you do that right, you are going to have, that's A, that's 26A. On 26C, if you do that right, you are going to get 11 waters. Okay? C's the harder one, I'm going to tell you that right now. C's the harder one. Just telling you. Okay. And don't forget, well, you don't shut off the camera.
Nope.
Okay. So, when they, on this book, they'll talk about a reductant. Reductant just means the same thing as a reducing agent. And if you see oxidant, that just means the same thing as the oxidizing agent. Okay? So, they kind of go old school with that terminology. So, anyway. Okay, we're good.